Okay, so hello everybody. Today it's a pleasure to introduce Marino from University of Geneva, and he will talk to us today about renormalons, integrable QFTs, and resurgence. So thank you for accepting the invitation. Please.
Thank you for inviting me. It's really a pleasure to be in Dublin, even so virtually. So I'm going to try to give a general introduction to subjects in which I have been working for the last couple of years or so. Some of the topics I have been working on them even for a longer time. So let me start with some very basic observations that probably people should know about them, but I'm going to review them anyway. So my starting point in this talk is going to be perturbation theory. And one of the reasons that we do perturbation theory is that it's actually one of the few universal tools to do analytic calculations in quantum physics. And very often you are able to compute, say, for example, the ground state energy of an interacting physical system as a series in a power series in the coupling constant G. And this is very often to be a kind of very important starting point to understand a system. And we spend a lot of time in our lives learning about this and teaching our students about this in quantum mechanics, in quantum theory, and so on. But we also know, sometimes a little bit vaguely, we know that there are non-perturbative effects which are supposed to go beyond perturbation theory. And very often in quantum physics, these effects are exponentially small in the coupling constant. So there are, like, just to give you two examples of these non-perturbative effects, one of them is the tunneling phenomenon in quantum mechanics, which are exponentially small in h bar. And another important phenomenon is superconductivity, which is exponentially small. The energy of a Cooper pair is exponentially small in the coupling constant of the fermion system. So we are supposed to have both perturbation theory and non-perturbative effects in our physical system. And the question is how you combine them. So you usually expect that, you have a physical observable, you should, in a sense, combine both things, and naively you would think that you have to add both things. So you could say, okay, a physical observable is going to be just a perturbative series plus some exponentially small corrections which correct perturbation theory. So, for example, you have an observable E of G, which could be the energy of the ground state, for example, of a physical system. Then you will first have all these perturbative series, and then you will have an set of exponentially small corrections. And actually, when you actually do calculations, they typically go like this. You have a leading exponential here, then you have a power of the coupling constant of this type, and then you have yet another power series in the coupling constant G. So in a sense, the perturbative series that you computed is just the first perturbative series that appears in an observable, and then you will have tons of perturbative series appearing, and all are going to be exponentially damped by this exponential factor. Now, this is kind of very naive, and it turns out that making sense of this equation is actually very subtle and has led to many confusions. And perhaps the first context in your life when you have to really deal with exponentially small corrections is in the WKB method. And you have ever gone through a course on quantum mechanics where they explain the WKB method, people, become very kind of mystical about, things that can, connection formula that are true in one direction, but they are not true in the other direction. And there are all kinds of subtleties. And, this is a subject which is very often very kind of confusing. And it's not just confusing when you teach it, it's actually confusing even in the papers. So part of what we should learn in this colloquium is, how to solve actually these confusions, which are, as I said, they go back to elementary issues like WKB expansions. So the first question you should ask anyway is, why is perturbation theory insufficient? I mean, why you should add all these exponentially small corrections? After all, in many cases, for example, when you work with analytic functions, we know that the perturbative series, the series expansion, is actually a good representation of the function. Well, the reason that perturbative series are not really well-defined functions, are not really sufficient, is that they are not really well-defined functions. They are not analytic functions. And what one finds in practice is that the coefficients of perturbative series grow in general factorial. Now, if a series has a factorial growth, it has a serious radius of convergence, and then it really doesn't define a function. So when you write such a series like this, you're not really writing anything that makes mathematical sense, because this series is going to give you infinite for any value of G. Okay, if you try to sum it. So what you have to change your framework and not thinking about convergent series, but thinking about asymptotic series. So if you think about this as an asymptotic series, then this is actually a correct result, and this is why perturbation theory is useful. Perturbation theory gives you asymptotic approximations to observables. These series are asymptotic to the correct results, and if you really want to get numbers, you can do it by using something that is called optimal truncation. So this means that if G is sufficiently small, you can keep a few terms of this expansion to get some approximate answer for your observer. Okay. So with asymptotic series, the first thing you have to really take into account is that you will never get an exact answer for your problem. Okay. So this is also very important. So asymptotic series never give an exact answer, and actually they involve exponentially small errors. Okay. So when you have an asymptotic series, the best you can get is an approximation to your observable, which is going to be true up to exponentially small errors. So this means in particular that this expression that I wrote before, in which you have this asymptotic series plus an exponentially small correction, actually doesn't make sense. I mean, no mathematician would actually trust this expression. It's actually completely meaningless in classical asymptotic theory, because you are mixing something which has an exponentially small error with something which is exponentially small, and it's of the same order of the error. So essentially, adding this doesn't make any sense. Okay, and in a sense, making sense of this expression is one of the things that physicists and mathematicians should actually know how to do. Okay, and this is what we're going to. Something I'm going to try to explain a little bit in this talk. But you see what? So the first lesson of these few slides is that this idea that you take perturbation theory and you add non-perturbative effects to it. I mean, on the face of it is completely meaningless. Also, people keep repeating it. It's just you just think about it, doesn't make any sense. So you have to do better than this. Okay, you have to use a more sophisticated machinery if you want to make sense of that statement. Now, one could suspect that these perturbative effects are anyway there, and they are related to the fact that the perturbative series is factorially grown. Okay, and one could suspect that there is a connection between these two things, and this was actually pointed out long ago by Freeman Dyson as far back as 1952. So Dyson wrote this famous paper, which I think has one equation and 2 pages or something like that, where he actually pointed out this. He pointed out that the fact that there are exponentially small corrections in quantum field theory is because series are factorially divergent. And the intuition of Dyson was made quantitatively much more precise by Lamb and Bender and Wu in the early 70s in the context of quantum mechanics. So what these people found following the insight of Dyson is that the growth of perturbation theory contains information about non-perturbative effects in the theory. So these two things, perturbation theory and non-perturbative effects, are not unrelated. They are related in a kind of quite precise way. And this connection between factorially divergent perturbative series and exponentially small correction has evolved into a general mathematical framework, which it's known as the theory of resurgence. And maybe you have heard this name because people write papers on this. And the name resurgence comes precisely from this connection. The idea is that non-perturbative effects resurge in the perturbative series. Okay, so and this is why the name of research comes from. So the name of resurgence is pointing out to this connection between the perturbative series and the exponentially small effects. So what I'm going to do first is to give like a quick review of the kind of mathematical technology that is needed in order to make sense of these statements. Okay, so in order to do this, I'm going to introduce some tools from the theory of Borel resummation. Maybe some of you have been exposed to it, but I'm going to go through them in some detail. Okay, and once I explain this technology, I will be able to make a more precise statement. I will be able to make more precise everything I have said. Okay. Okay. So now this is going to be a little bit. This is going to be, in a sense, the most arid part of the talk, but it's actually something good to learn, which is the Borel technology, the Borel method. So what is the Borel method? Well, the Borel method is actually a systematic way of making sense of something that doesn't make sense, which are factorially divergent formal power series. So in physics, we often have to deal with factorially divergent formal power series, and the Borel method is actually a method to make sense of them in some appropriate circumstances. So let me give you kind of the more general construction. So suppose you have a factorially divergent formal power series in the variable z, and these coefficients an are supposed to grow factorially. Okay? So this is the starting point, this factorially divergent power series that could represent a physical observable in a quantum theory. Now, the first step of the method is to do a Borel transform. And the Borel transform is just a way in which you very brutally remove all this factorial divergence. So the thing you do is you divide every coefficient an by n factorial. And then you create a new series in a different variable zeta. So this series, the coefficients of this series are no longer factorially growing because you have removed the factorial divergence by hand. And then this function, you can now try to do a Laplace transform of it. Essentially, you can try to integrate it about the positive real axis with an exponential weight. And in favorable situations, you obtain a function, which is called the Borel resummation of the original series. And it's actually a trivial exercise in integration to show that this function, if it exists, has the original power series as its asymptotic expansion. So the Borel resummation method is a method in which you start with something that doesn't make sense, which is a formal power series with factorially divergent coefficients. And at the end of the day, if you are lucky, you will find a function such that the series that you started with is an asymptotic approximation to your function, but you end up with a true function. Okay? Now, this is very beautiful, but it doesn't work all the time. And there are kind of very clear reasons why this wouldn't work. This cannot work all the time. So let me first point out that the Borel transform is a function which is typically analytically at the origin. So this is very good because you started with a function which is with a power series doesn't make sense. And now this Borel transform at least is an analytic function at the origin. And then you can use all your knowledge of complex analysis to actually study this function. Now, what you find is this function has a finite radius of convergence. And this is actually because you have removed this factorial growth. And then once you start moving away from the origin, you will find all kinds of singularities in the complex plane. In this complex plane, I will call it sometimes the Borel plane. And these singularities can have different effects. So, for example, if you have a singularity which is on the positive real axis, then this Borel transform is going to give you trouble. Because as I was telling you before, in order to do this Borel resummation, you have to integrate this function over the positive real axis. So every singularity on the positive real axis will be a problem for this method. Okay? And that's why this method cannot be applied all the time. Now, there are some cases in which life is actually very nice and the Borel resummation method works very well. So let me give you an example which probably you have studied in your undergraduate or graduate courses in quantum mechanics, which is the quartic oscillator. Okay? So you start with a Hamiltonian, which is the harmonic oscillator Hamiltonian, and then you introduce a quartic perturbation with a coupling constant G. Okay? So Gx to the 4. So this is a problem that we give to our students, and we tell them to calculate the first or second order terms of the, say, ground state energy as a series in G. And this is an relatively elementary exercise, so you can compute it. And then what you will find in units in which h bar is equal to 1, you will find that the ground state energy of the system is 1/2, which is the ground state energy of the harmonic oscillator. And then you will have a power series in G. And this power series in G is perhaps the first example of a divergent series in quantum theory. And we never tell our undergraduate students that the series that they're going to obtain doesn't make any sense. Because we don't want to discourage them, but it's actually the case. This series doesn't make any sense, and actually the coefficients grow factorial. Okay. However, this series has a Borel transform which has no singularities on the positive real axis, and then this Borel resummation procedure actually goes through. And not only goes through, but it actually gives you exactly the spectrum of this system. So you want to calculate the ground state energy of this system, you can compute as many terms as you can of this series, do this Borel resummation procedure numerically, which you can do. There are many techniques to do it. And then you will get a very good approximation to the actual ground state energy of the system. There is actually a theorem that says that if you actually do this, the Borel resummation of the series is exactly the ground state energy of the model. So this is really very, very good. This is as good as you can get. And you see, this is a case in which perturbation theory, it's really not. You don't really need non-perturbative effects in this example, okay? But of course, life is never as nice as in this example, and there are many other cases in quantum mechanics and quantum field theory where you cannot really do that. Just doing a standard Borel resummation is not conclusive. And as I was pointing before, one of the reasons is that you might have singularities of this Borel transform on the positive real axis, and then you will not be able to do your Laplace transform. Okay. So this is the case in which people said that the series is not Borel summable. And essentially, maybe like 50 years ago, people, this would be the end of the discussion. Okay, this series is not Borel summable. We cannot Borel resum it. Okay, let's go home and try something else. Okay. But, one of the things that people did in the theory of resurgence is to try to go beyond this obstruction. And one idea that probably is an idea that physicists use, but was formalized by Jean Écale, which was one of the creators of the theory of resurgence, is the following. Écale said, well, you see, singularities, if you are a complex analyst, you're not really worried about singularities, because you see, if you have an integral and you have a singularity in the integration contour, I can always avoid it by moving my integration contour a little bit away from the singularity. Okay. Actually, I can do this in two ways. Imagine that I actually have singularities on my positive real axis, and I want to do this integral. Well, I can avoid the singularities by going over the singularities, or I can avoid the singularities by going below the singularities. So I can define two different Borel resummations, which are called lateral Borel resummations, by deforming the integration contour either on top or below. Okay? And this gives you a way to actually define something in these theories in which there are singularities in the positive real axis. But of course, this is not really, this is not really the end of the story, because now, in a sense, you have too many things, right? You have now two choices about how to resum this, and the result is ambiguous, because when you have two ways of doing a resummation, the result might not be the same. And actually, it's known that if the Borel transform has a singularity at a given point, these two lateral resummations are not only different, but they differ by an imaginary exponentially small quantity. Okay, so your problem is that now, once you have this singularity there, you not only have an ambiguity, but this ambiguity is even imaginary. So it means that if you're looking, for example, for a ground state energy, which is a real number, this ambiguity is going to hit you on the face, because it's really a bad thing for your calculation. So anyway, what you can, in spite of all these problems, you can think about this equation as a very important equation, because it's telling you another way in which exponentially small things pop out in your calculation. So you have your perturbative series, you try to do the Borel resummation, you cannot do it because there is this singularity, then you decide to use this deformation of the contour, you still don't get the right answer, but you know that this singularity is telling you something about an exponentially small quantity appearing in your theory. Okay, so this is actually a signature of a non-perturbative correction. This is one way in which you can actually detect a non-perturbative correction, by doing these two lateral resummations and seeing that the difference is an exponentially small quantity. Okay, so actually very often what happens is that the series that you are computing here is an actual exponentially small correction to your theory. Now, moreover, this exponentially small quantity that you find in this way has another implication, which is that it allows you to obtain the large order behavior of the original perturbative series. So remember that all these calculations were done based on a perturbative series with coefficients an, and if you look about this expression, you will see that it's determined by the location of a singularity at A, a coefficient and an exponent B, some coefficient C1, and so on. And it's actually a very elementary calculation to show that if you have such a difference between these two resummations, then the large order behavior of the original perturbative series is completely determined by this data. So A appears here, B appears as a correction to the factorial. Remember that this series is factorially divergent. So this is the factorial growth. The coefficients of the perturbative series appear in subleading corrections. The overall coefficients appear here and so on. So let me summarize what I have explained so far. Essentially, what I'm telling you is that I have tried to make mathematically concrete this idea that perturbative series and non-perturbative corrections are intimately related. And there are actually three ways in which you can see this. So if you take a perturbative series, the first thing you can try to do is to see what is its large order behavior. So how these coefficients grow when n is large. And the growth of these coefficients is giving you all this information, which actually is telling you about this exponentially small correction here. Equivalently, you can think about these non-perturbative corrections as singularities of this Borel transform. Remember that this difference happened because the Borel transform has a singularity in the positive real axis. So these singularities, through their location, are telling you about exponentially small effects. And actually, the location of the singularity gives you the strength of the exponential effect. And so all these two things give you information of exponentially small corrections, and this is essentially the idea of resurgence. Okay. So now you can ask now, okay, if you are giving a physical theory, if I take a perturbative series, there might be cases in which I don't have singularities on the positive real axis, but in general, you would like to understand all possible singularities of these functions, in particular the ones that come from the positive on the positive real axis, and you would also like to understand what is the physical meaning of this singularity. Okay, so these singularities are telling you about exponentially small corrections. So you could ask yourself, what is the physics behind these singularities? Okay. Now, before I discuss the physics of this singularity, let me actually mention that now that we have this technology of Borel resummation, we can make sense of this equation I started with. Remember that I told you at the very beginning that we expect observables in quantum field theory to be given by the sums of perturbative series plus the exponentially small corrections that correct this perturbative result. Now, this equation doesn't make any sense, but you can think about this object as a formal object, and this is where mathematics is useful. You don't have to think about this as something giving you a number. You think about this as a formal object, as a combination of things which doesn't make sense, as a collection of numbers, which includes both the perturbative information and the non-perturbative information. And this formal object, which is a series in G and a series in e to the minus a over G, this is what people call a transeries. It's just simply this. It's a series which has both a parting, a kind of formal power series in the coupling constant, and a formal power series in the exponential of the coupling constant. See, this is called a transeries. Now, this is a formal object, but there is a way of going from this formal object to a number. And this way of doing this is Borel resummation. If you do, even if these things are have singularities, you can always do lateral Borel resummations to avoid them. Okay, so the statement that you find in many examples is that observables in quantum theory are actually given by lateral Borel resummations of this type of transit. Okay, so for example, here I have lateral Borel resummation of the series, plus I remember I told you that there is another factorial divergent series attached to this exponential small correction. You keep this factor as it was before, and then you do the Borel resummation of this other series. And Borel resummations, lateral Borel resummations are always well defined, and you can always get a number from here. But now you will say, hey, but you told me that lateral Borel resummations are ambiguous, okay? And they differ in exponential small corrections. And then the answer to this problem is the following. Okay, let's adjust the coefficient of this exponentially small correction so that it cancels the ambiguity of this perturbative series after lateral Borel resummation. So from the equations I showed you before, it's very easy to see that the only thing you have to do now is to say that these two constants, you can do the calculation in two ways, but then these two constants will have to have an imaginary piece in order to cancel the imaginary part of here. And then these two constants actually have to differ in minus I times S, where S is the coefficient that appear here. Okay. So essentially, what this is telling you is that if you do lateral Borel summations and you put the right exponentially small corrections in your trans-series, you will be able to obtain exact results for your observables. Okay? And essentially, the belief is that every object in quantum field theory which has a perturbative expansion, which is asymptotic, can be upgraded to an exact answer in terms of a Borel resum transit. Okay? So as long as you have a perturbative series to start with, you should be able always to upgrade this by adding these exponentially small corrections, and then you will obtain an exact representation. Here now we have an equality. This is really an equality. And one thing that you learn is that the coefficients of these exponentially small corrections are very subtle because they are not really intrinsically defined. This number here is not intrinsically defined. This number depends on your choice of lateral resummation here. And so this is intrinsically ambiguous, and the ambiguity in this coefficient should be such that you cancel the ambiguities coming from the lateral resummation. So this is really a very important lesson, is that in quantum theory, the strength of an exponentially small correction is not really well defined. You can only define it if you tell me before which choice you are making for your lateral resummation, if you are resumming from above or from below. And this is a very important thing because people were not aware of these subtleties like maybe 50 years ago. And for example, the theory of the WKB method was in a really dismal state because of people not being able to actually address these subtleties. And if you read, for example, the review on WKB method in 1917 by Michael Berry, it's just full of confusions. I mean, it's not the confusions of Berry. Berry was very aware that there were these problems there. But you see that, people essentially didn't really understand how to use exponentially small corrections in the WKB method. And we are talking here about the WKB method, which is supposed to be an elementary thing. But really, if you really want to understand the WKB method, you really have to do this. Otherwise, you will get the wrong formula. So these type of ideas are very important. And let me actually also mention that this idea that the trans-series constants are really ambiguous, this was actually pointed out by François David in the context of quantum field theories, and I might come back to this later on. Okay, so this is in a sense the most technical part of the talk, so maybe there are questions at this point. Okay, so as I was, so just to summarize, you have perturbative series. Perturbative series might have, you have to resum it if you really want to have an exact expression for your observable. And if you want to really get something exact, you will have to add these exponentially small corrections, but you have to be careful with the singularities because you will have to do this lateral resummation and so on. And very importantly, you can make a diagnosis of the non-perturbative effects of your theory just by looking at the singularities of the perturbative series. Okay, there might be more non-perturbative effects in your theory, but already the singularities of the perturbative series are part of the non-perturbative effects you have to take into account. Okay, so at least the non-perturbative effects of your theory, at least some of them are already attached to these singularities of the perturbative series. So the first thing, if you don't really know much about the non-perturbative structure of a physical theory, of a physical quantum theory, the first thing you can do is to really try to understand the singularities of this Borel transform of the perturbative series. So you try to exploit as much as possible the perturbative information in order to deduce non-perturbative information. Okay, so this is in a sense one of the methods of resurgence. If you want to understand non-perturbative sectors, start with what you know really well, which is perturbation theory. And then, maybe this is not enough, but this is already the starting point. Okay. So the question now is, as I was mentioning before, what is the physical origin of these Borel singularities and of exponentially small corrections? Now, there is a very famous source of exponentially small corrections in physics, which are called instantons. Okay. So instantons appear already in quantum mechanics. They are solutions, with finite action to the Euclidean equations of motion, and they represent additional sectors of the path integral beyond the trivial sector, and they really typically give you exponentially small corrections to your quantities. Now remember that singularities, so these exponentially small corrections will lead very generally to singularities in the Borel transform. Now you can actually ask, okay, since we know that these singularities are related to the growth of perturbation theory, what are instantons telling you about perturbation theory? Now, what instantons are telling you is the growth of perturbation theory due to the proliferation of diagrams. Okay? So when you do perturbation theory, it turns out that at loop order n, when you are doing a calculation with n loops, it turns out that there are n factorial diagrams that contribute there. So just the growth of Feynman diagrams already gives you a contribution of n factorial to the coefficients of your series. And instantons precisely tell you about the growth of the total number of diagrams. Still, I have to say that if you really want to understand instanton type singularities in very generally, it's actually not so easy. So in quantum mechanics, this is really well understood. And if you go to quantum field theory, it's not so well understood. I mean, there are also, of course, supersymmetric theories, which things are in a sense much simpler. But if you think about generic quantum field theories, it's not so easy to understand the structure of singularities due to instantons. But there is one example in which we know a little bit what is going on, and these are topological theories which have a non-trivial perturbative series. So these are in a sense like integrable models, and in particular, I'm thinking about complex Chern-Simons theory. And in Chern-Simons theory, or its complexified version, you can really understand this structure in actual, in really detail. I have worked myself on this, and this has ramifications for the studies of three-manifold invariants and so on. Okay? But we are not here, in this talk, we are not interested on these topological field theories. So we would like to understand, more physical theories. So the question you can ask, if you consider more general theories, are all singularities due to instantons or not? Well, the answer is unfortunately no. So people found in the 1970s, 1980s, they found a new source of singularities for this Borel transform, which is different from instanton singularities, and people didn't really know very well what they are, and I think Toft called them Renormalons singularities, because these Renormalons singularities appear in renormalizable theories. Now, remember, so why instanton singularities are different from Renormalons singularities? Well, remember that instanton singularities are telling you about the growth of perturbation theory due to just the sheer proliferation of diagrams. Now, it turns out that when you have in many physical theories, in many renormalizable theories, it turns out that there is a source of factorial divergence which is not related to the growth of the number of diagrams. It turns out that there are diagrams, so at each loop, there is always one special diagram which gives already an n factorial contribution. And why is so? Because when you compute a Feynman diagram, you have to do something which is integration over the momenta. And it turns out that there are some special types of diagrams that after integration over the momenta will give you an n factorial on your face. So for example, there are these type of diagrams called bubble diagrams, in which if you have like a coupling constant which has some sort of logarithmic dependence on the momenta, an effective coupling constant with a logarithmic dependence on the momenta, just by integrating over the momenta, you will get n factorial. So essentially, this identity is actually the key to understand why, just simple mathematical identity is the key to understand why integration over momenta can be a source of factorial growth. And this is different from instantons. So people really were very confused about this. For a long time, people thought that instantons would be just the only source of non-perturbative corrections. And then these renormalons were, in a sense, like spoiling the party. Right? People were doing all kinds of instanton calculations, and then, these renormalons essentially, were really not very welcome because they are really not as easier to understand as instantons. So, in spite of that, very clever people like Parisi and Toft that got Nobel Prizes, not for this, but they are clever people for many different problems. So these very clever people even if these renormalons were a little bit complicated, they were able to make a general conjecture about what would be the most important characterization of these singularities. Remember that these singularities are singularities in the Borel plane, and then Parisian thought to look at theories which they were very interested in, which are asymptotically free theories. Okay, and then they were able by doing some sort of heuristic arguments to make a conjecture on the location of possible Borel singularities of physical observables in these theories. And their argument was that in the Borel plane for the perturbative series of asymptotically free theories, the singularities are always at integers divided by 2 times beta 0. And beta 0 here, remember that we are talking about asymptotically free theories, beta 0 is the first coefficient of the beta function, the first non-trivial coefficient. Now, if you have singularities here at these locations, then remember that when you have a singularity in the Borel transform at these locations, there will be an exponentially small effect associated to them. And then by exponentiating this, divided by the coupling constant, evaluated at a scale mu, you will see that the strength of these non-perturbative effects is of the order lambda over mu to the d. So lambda here is the dynamically generated scale of these asymptotically free theories. Mu is the momentum at which you are doing your calculation, and d is essentially the power of the lambda scale. And then, people were, at the same time, people were actually studying condensates in asymptotically free theories, which were vacuum expectation values of operators. And then people thought that these singularities were actually giving information about these condensates. So these Borel singularities due to renormalons were giving you non-perturbative information about the true vacuum of asymptotically free theories. Okay, so that's why these are in a sense very important objects to look at, because they are supposed to give you very important non-perturbative information, which is actually not reducible to instants. Okay? So this is really a different source of non-perturbative information. So most of these results, I have to say, were actually have been conjectural, and it's actually, although they have been around for a long time, it's actually good to really, at some point, to sit down and really look at the actual evidence for all these claims. Okay, so the first question you should ask is, okay, this is the statement about the location of singularities. How do we know that this is true? How do we know that there are singularities in the Borel transform of perturbative series in quantum field theory at these locations? And you should actually be skeptical about these claims, because it's very hard to compute perturbative series at large order in quantum field theory. I mean, in QCD, it's very hard, for example, to compute things beyond, say, 6 or 7 loops, right? So if these singularities, for example, you want to detect them from the large order behavior of perturbation theory, then clearly having 5 or 6 terms is not enough. So you really want to, for example, in quantum mechanics, when you really want to look at the singularities of the Borel transform, you typically use 100 or 200 terms. So there is no way that you will get as many terms as that in QCD. Okay. So how do we really know that all this is actually true? So let me discuss then what is the evidence for renormalons. Now, there are 2 sources of evidence for these singularities. One are large chain approximations, and the other are numerical calculations. Now, one very interesting thing about these renormal singularities is that when in theories which admit a large chain top limit, these singularities survive in the large chain limit. And this is in contrast to instanton corrections. Instanton corrections do not survive the large chain limit. So you have a Borel singularity, which is due to an instanton correction, is going to be a scale like n. And when n goes to infinity in the top limit, this singularity just goes to infinity. Equivalently, the exponentially small correction of an instanton, of an instanton with a small instanton number, will also go away when n goes to infinity. However, instanton correction, renormal corrections are essentially like nth roots of instanton corrections. So if you have an exponentially small effect like this, remember that in gauge theories, for example, they say a large n, sigma model or QCD, the beta function is case like n, and then and then you will have an effect here that when you take n to infinity, keeping n times g fixed, this is going to still survive, and this is going to be of the order e to the minus 1 over lambda, where lambda is the top parameter. Okay, so our large n, these Renormalons singularities survive, and in particular, you can also understand them from these diagrams, from the diagrammatic perspective. A large n, typically only a special families of diagrams survive. So typically, these bubble diagrams that are the source of this factorial divergence are the only things that survive a large n, and you can actually obtain explicit results for Borel singularities. So many of the things that we know about Renormalons have been obtained in the large n limit. Now, another way, remember that another way of detecting location of singularities is by looking at the large order behavior perturbation theory. Now, so you could try to produce what I call a long perturbative series, many terms in a perturbative series, and try to see if actually the large order behavior of the series is actually dominated, is actually controlled by such a singularity. And there is actually an impressive calculation in pure Yang-Mills in which people do what is called lattice perturbation theory. So they do a numerical calculation of the perturbative series, and they can go up to order 50, I think. And when you do that, you actually confirm the first Renormalon singularity of Parisian top. You can actually check that remember that Parisian top tell you that they are going to be, these are the generic positions of singularities. In general, you expect to have many singularities in your positive real axis. And if you look at the larger behavior of a perturbative series, you typically only detect the first singularity. But they actually detected it, and it was according to the predictions. Okay, so this is also some evidence, which is actually quite recent. These papers by Bauer, Bali, and Pineda are not even, I don't think they are even 15 years old. So they are probably even 10 years old. So effective numerical evidence for Renormalons was obtained only very recently. Okay, but you see, all these things are numerical. And then, you only see the first singularity, or they are large n. And the question is, can you actually have information which is analytic and actually maybe at finite n? Because, large n limits, a large n, many details of the theory, many subtleties get lost. And the question is if you can actually have analytic control over all these theories. Now, of course, also, another way to put these things is that, not everybody interested in the formal properties of quantum field theories are able to do a Monte Carlo calculation like this one in the lattice. So, is there any other way to kind of make progress, right? Because this, after all, understanding Yang-Mills theory, pure non-supersymmetric Yang-Mills theory is actually a hard problem. So what should you do? Well, then, there is a citation by Freeman Dyson that I like a lot. It says that when you are very tired of working on insoluble problems, what you can do in order to refresh your imagination is to go to the beautiful world of one dimension. And according to him, this is better than a dose of LSD. And he actually wrote this in Physics Today in 1967. And in the article where he wrote this, you can see this drawing of somebody living in one dimension and having his imagination, all excited as under the effects of LSD. Okay, so of course, this is 1967, it's the summer of love, and apparently Dyson was not completely alien to the atmosphere of the period with psychedelic drugs and things like that, and then he was recommending us to do this trip to the beautiful world of one dimension, and this is what we are going to do. Okay, so if you want to understand asymptotically free theories and you want to have a hope of doing analytic calculation, maybe the first thing you can note is that there are asymptotically free theories in 2 dimensions, which are asymptotically free, but they are also integrable. So their S matrix is exactly known. The 3 more important models that satisfy this property are the ON nonlinear sigma model, the Grosneve model, and the principal chiral field. There are some other models like supersymmetric versions of this, but these are the main the main models that I will have in mind. Now, you want to understand, if you want to understand this sort of perturbative properties, and you want to understand the emergence of non-perturbative effects, you have to choose a good observable. So this is an observable that you have to be able to compute this perturbative series, and at the same time you have to be able to use integrability techniques to calculate it. And one of the simplest observables that you can look at in this way is the ground state energy of these theories. But once you couple the theory to a chemical potential H through a global conserved charge. So essentially what you do is you take the standard partition function on a finite volume and a finite radius, and you deform your Hamiltonian, or you change your ensemble by adding a conserved charge of the theory coupled to this chemical potential. And then you define in the infinite volume limit a free energy that I'm going to call f of h, which is going to depend on h. And what is important to introduce h? Well, it's important to introduce h because you want to do perturbation theory and asymptotically free theory. You need a scale, an external scale that allows you to go to very high energies. Remember that in asymptotically free theories, you can do perturbation theory at very high energies. So in order to set the scale of very high energy, you need some additional a dimensionful quantity that you can turn, that you can tune. And this is actually the role of this H. Now this observable can be computed in standard perturbation theory when H is much larger than the dynamically generated scale. So this is high energies. And then you can actually compute a perturbative series in the running coupling constant, which is computed at the scale H. And then you get a perturbative series with numerical coefficients an that can be computed in perturbation theory, maybe not to very large order, but you can compute, say, at 2 or 3 loops. Now, of course, you can push this calculation to higher orders in some situations, but also, this is a calculation you could do in any theory. Now, what characterizes these theories is that they are integrable. So the question is, you can actually calculate FH using integrability. And it was actually pointed out by Polyakov and Bigman that you can actually compute this thing using integrability by using the exact X matrix and the Bethe ansatz. So this is not really like the thermodynamic Bethe ansatz, it's a kind of simpler version of the Bethe ansatz. As I said, this is was not noted really long ago. And essentially, what Polyakov and Bigman noted is that you can write down an integral equation which has all the information of this observable for you. So this is an integral equation of this type. So, for a quantity epsilon of theta, you can think about it as a density of Bethe roots. It's like a Fermi distribution of pseudoparticles for the theory. It involves H. H is part of the data, and it also depends on the mass gap of the theory, M. And then, this integral equation depends on some limits of integration B, but, they are fixed essentially as functions of H and M by this condition. And once you know this density of Bethe roots, you can calculate this free energy just by integration. Okay. Actually, you want to calculate FH numerically. I mean, this is just essentially trivial. I mean, you can write a program, with 5 lines that does this calculation for you. So you can solve this integral equation numerically and calculate FH numerically. So this is an observable for which we have really total control from the point of view of having an exact answer. Now, people have studied this observable a lot, especially in the early 90s. People realized something very interesting. Now, in an asymptotically free theory, is part of the definition of asymptotically free theory that the mass gap has to be proportional to the dynamically generated scale in a given scheme, and this proportional and all the masses of all the particles have to be proportional to the dynamically generated scale. So it's a non-trivial question to actually do this calculation, because the dynamically generated scale lambda is typically defined in a perturbative scheme, and the mass gap of the theory, for example, the smallest excitation, the lightest excitation of the theory, is really extremely non-perturbative. So calculating the proportionality constant between these two things is very hard in general, but using integrability and using this observable f of h, Hasenfratz, Niedermayer, Michele Maggiore, and other people were able to obtain it for many of these integrable models. And they actually found a very nice relationship like this, which is actually valid for any, is valid for any n. So this is actually a proof of concept that masses in asymptotically free theory are proportional to lambda, to dynamical generated scale. So this was one of the uses that people did of these integrable models in the context of physical questions related to asymptotically free theories. Now, recently, what we realized together with other people is that this is also an observable, which is an ideal testing ground to learn about renormalons and about non-perturbative corrections. And one can hope to exploit integrability to obtain detailed information about the Borel singularities and the trans-series information of this observable. Now, in particular, as I said, this observable has a non-trivial perturbative series. So this is an observable in asymptotically free theory. So you could now ask what are the singularities of the Borel transform of this power series, and you could try to see if these singularities are satisfy, for example, the conjectures of Parisi and Tov, and what are the kind of non-trivial information you get. And in particular, f of h should be hopefully given by the Borel resummation of a perturbative series plus some exponentially small corrections, which are going to tell you about instanton and renormalon effects in this theory. Okay, and this is something that you can try to use integrability to decode this observable in terms of path integral data. Okay, so this is actually something that has been done in the recent couple of years, and essentially one thing that you can do is to use all the methods that people use in more complicated theories. You can use large n and you can use numerical methods, but in both cases, integrability is going to enhance your performance. So for example, the 1/n expansion, usually when you do this in standard theories, essentially they only give you some sort of handle on the perturbative series. So essentially large n tells you that only a few diagrams are going to dominate a large n, so you can focus on them and so on. Now here, we have also a Bethe-Ansatz solution. So we can try to actually understand the 1/n expansion directly at the level of the Bethe-Ansatz. And this was done already some time ago by people that look at this type of problems. In particular, it was a very insightful paper by Fatev, Kazakov, and Bigman on this problem. And when you do this at large n, you can actually get very precise information on the Borel singularities at leading order in 1/n. Okay, so you really get nice equations that determine the location of Borel singularities at 1/n. Now, you can also try to use numerics. So you can try to extract as many coefficients of the perturbative series you can, and then look at the large order behavior of these coefficients to locate the Borel singularities. Now, again, if you wanted to use a standard techniques in quantum field theory, you wouldn't get very far. But here, what is very interesting is that if you use again the Bethe-Ansatz, you can actually extract the coefficients of the perturbative series up to very large orders. So you can actually go say, for example, if you are happy with numerical values, you can go to 2,000 loops, okay, using the Bethe-Ansatz. Okay, and this is a method that is a really very beautiful technique which was introduced by Dimitrov Volin. It's a highly non-trivial problem to extract the perturbative series from the Bethe-Ansatz, and this has led to very interesting results on the Borel singularities. But again, usually it's not so easy to actually get information about all of these singularities. And again, it's numerical, so it's not so clear what you get. So recently, what we found is actually a method that allows you to understand the singularities of the Borel singularities of these theories analytically and at finite n. And I'm not going to give you details on this. It's actually relatively complicated. But for people who are, for example, familiar with the papers of Samolochikov on these subjects, there's this famous paper of Samolochikov which calculates the relationship between the mass and the perturbation parameter in sine Gordon models and perturbation of conformal field theories. So this method is essentially is what we used, but we extended to asymptotically free theories. So some logic of use it in the context of super renormalizable theories. But if you extend this method to asymptotically free theories, you can actually obtain this information. So what we were able to do was to actually get analytic results for the exponentially small corrections to this observable. So essentially what we were able was to decode this free energy in a perturbative piece plus exponentially small pieces. And remember that when you do this, you have to find results which are ambiguous. And this is actually what we find. And it's a very beautiful property of the Bethe-Ansatz equation that it gives you this, it has built in this intrinsic ambiguity due to exponentially small corrections. And this is actually something new with respect to what Samological had done. So just let me give you one example. You take the O3 sigma model, which is in a sense the simplest integrable model that you have. If you consider the normalized free energy as a function of h, we saw that it has this perturbative part, and then it will have a first non-perturbative part, which is typical of a Renormalon effect, okay? And then it will have a piece which is ambiguous and imaginary, as it should, and then it will have a real part as well. So this part here is a typical Renormalon effect, and you can actually understand it from diagrams, and this we also did. Now, this part here, we suspect is an instanton correction. It's really due to the instantons of the O3 sigma model. Remember that the O3 sigma model has instantons on top of Renormalons. And actually, it's not so. It's actually something that we conjecture, but we don't have still a first principle derivation. But what is, I think, very amazing from this type of calculations that you have an observable in quantum field theory, and you can really decode it in terms of perturbative series plus exponentially small corrections coming from Renormalons and instantons, okay? Possibly. So it's actually quite non-trivial. I mean, if you think about it, there are not that many observables in quantum field theory in which we can actually do this. We can actually see all these observables. I mean, in non-supersymmetry theories. In supersymmetry, once you have supersymmetry, everything changes very much, right? But for bosonic models, it's actually quite exciting for us to have these exponentially small corrections really being completely explicit. Now, once you do that, you can actually go back to the problem of Toth and Parisi and say, where are the Borel singularities? Now, what we found is that actually the general form of Toth and Parisi is not actually true for these observables. And we found something very interesting. Now, in the Gross-Neve model and the principal chiral field, it turns out that there is a first Renormalon singularity at the expected location. And then there are infinite tower of Renormalon singularities which are not located at d over beta 0, but d over beta 0 times a correction which vanishes at large n. So essentially the Toth and Parisi result is really a large n result. It's not a finite n result. And this was one of the important points of doing a calculation at finite n. We can see this effect that you cannot see at large n. So when you take the large n limit, this correction disappears and you get the picture of Toth and Parisi, but not a finite n. And there is this very interesting fact that there are two singularities which actually collide when n goes to infinity. And this is a type of behavior of the Renormalon singularities that I don't think was anticipated by people working on this subject in more realistic models. So the structure of Borel singularities is more complicated. So this is for Gross-Neve and principal chiral field. Now for the OM model, the picture is very different. We have a Renormalon singularity here, and then we will have singularities which grow like n, so they are proportional to n. So these actually go away when n goes to infinity. Notice that when n is equal to 3, this singularity, which is of Renormalon type, collides with the first singularity of this tower. And we believe, because of this n factor, we believe that these towers are actually due to instantons, but we still don't have a concrete picture. So we now have all these exact results, and the question is, what is the path integral interpretation? I mean, if you think about it, we know from the path integral how to do perturbation theory. people in the 70s developed instanton calculus to try to make sense of exponentially small corrections. But apart from supersymmetric theories, we don't know that much about instanton calculus. And we know that instanton calculus is very ill-defined due to infrared divergences in many realistic models. Okay, so I think these exact results in these asymptotically free theories in two dimensions, some of them which have instantons stable or unstable, might be an actual way of understanding saddle points in path integrals in more concretely. Because if you are able to do a path integral calculation, you should be able to actually detect, for example, these instanton effects. Okay, so let me conclude. I think I think this topic really goes to the basis of quantum field theory. And the first lesson is the following. Conventional perturbation theory is just the type of the iceberg of what really comes from a quantum field theory. A quantum field theory should have perturbation theory plus an infinite series of exponentially small corrections which are there. Okay, so conventional perturbation theory should be replaced by what I would call resurgent perturbation theory, in which you don't really calculate series, you calculate trans-series. You calculate perturbative series plus exponentially small corrections. And this framework seems to be powerful enough to actually understand realistic quantum field theories, condensed matter examples, and so on. So I think it is probably a true statement that observables in quantum theory which have an asymptotic perturbative series can be expressed exactly as Borel-Brisson trans-series. And I think this is a very interesting point of view on quantum field theory. Now, what is actually dramatic is that we do not really know how to compute exponential corrections. I mean, you take your favorite book on quantum field theory, you can compute, you can follow the rules, compute the standard perturbative series, but there are no rules to compute these exponentially small corrections in general. Okay, so instanton calculus was developed to supply this, but renormalons in particular are much more subtle because they do not seem to be in general described by saddle points of the path integral. So, for example, if you want to calculate renormalon contributions for this observable of FH, there is no such a thing as renormalon calculus to calculate these things. So this means that when we calculate things like this using the Bethe ansatz, some of these things we don't really know how to calculate in quantum field theory. I mean, we don't really know how to calculate from first principles without relying on integrability. And I think this is really a huge gap in our knowledge of quantum field theory. We really don't know quantum field theory well enough to go beyond perturbation theory in general. Of course, you can, in some models, you can say, oh, I don't care, I use lattice, I use integrability, and so on. Yes, but you don't really know how to complete your textbook on quantum field theory by going beyond perturbation theory. We don't really know. And I think this is really a very important problem. And people were actually thinking about that when people like Toft and Parisi were thinking about renormalons. They were actually trying to think about how to go beyond perturbation theory. Now we know a little bit more, but this is still pretty much unexplored. So these are really unexplored new sectors of physical theories, which we do not really know. And I think integrable models are very important because, when you don't know much, you have to really rely on things which are very, very trustable. And integrable models are really should be signposts for these developments. So for example, any kind of first principle calculation in the O3 sigma model should be able to reproduce this result from integrability. Okay? This is a signpost for any possible calculation of instantons and renormalons in this model. So it's very important to know what you should get if you were ever able to get the right method, right? And that's why integrability is so important, because it really gives you hints, it gives you some lights in the darkness that can actually guide you in order to make progress in this problem. So I hope I have convinced you that this is a very basic problem in physics, and thank you very much for your attention.
Thank you very much for the very nice talk. So let's thank Marcos for the very nice talk. And are there any questions? Please just unmute yourself if you
So I do have a question. So the integrable models you're looking at here are the integrable field theories in 1+1 dimensions. But with ADS-CFT, as for example, N=4 sweeping mills, it's supersymmetric, of course. But that would be an integrable theory in 4 dimensions, where people have been able to use integrability techniques to compute things exactly, or at least for intermediate coupling. Could those also be useful for you to learn some things? And would something change if you would do these things in 4 dimensions instead of 2, for example?
Well, the thing is that N=4 superjamils has so much supersymmetry that you don't have renormalons. You see, N=4 superjamils is a finite theory, so there is no running coupling constant. So all these log effects that you find are actually not there. And that's why, for example, the 1/n expansion, order by order in 1/n, perturbative series in jam mills are actually convergent series, right? And they are not divergent, they are convergent, order by order in 1/n. So all these results on integrability in the planar limit of N=4 superjam mills, they tell you absolutely nothing about the renormalon problem, okay? Unfortunately. So that's why I'm not looking at that. I'm not looking at that because I'm not going to learn anything about renormalons by looking at N=4 superjam mills. Supersymmetry is too special theory. It's a theory in which there are no renormalons, and then all these non-perturbative effects are due to instantons. So in a sense, it's more like quantum mechanics, right? All these renormalons was this kind of new non-perturbative effect that people found in the 70s, and which is very mysterious because it's not really described by saddle points. Now, in N=4 superjam mills, eventually, I would believe that any non-perturbative effect, a weak coupling is going to be due to instantons. So that's interesting in itself, but this puts N=4 superjam mills more in the category of, say, Chern-Simons theory, or that in the category of 2D of QCD. And what is interesting is that these old-fashioned 2-dimensional models know more about this problem than N=4 superjam mills. So the old-fashioned integrability of 2-dimensional models, since they are asymptotically free, it's much more interesting in order to look at this problem. Of course, people already, François David, for example, who wrote very important papers on renormalons, he was using 2D sigma models in order to understand it, but he was using mostly 1/n expansions, not really integrability. So this idea of using integrability of 2-dimensional models to learn about renormalons and exponentially small corrections is actually quite new. It's something that happened in very recently.
Okay, thanks.
Can I ask a question?
Sure.
So in the realm of integrable quantum field theory in 2 dimensions, sometimes there are dual pairs. So in this case, is it obvious that renormalons will map to renormalons, or it's more
dual pairs?
Sorry?
What kind of dual pairs?
I don't know. I have in mind, for example, Sine-Gordon Turing model. Or...
Yeah, but these are super renormalizable theories. So there are no renormalons there. Super renormalizable theories might have renormalons in the case when you are doing the perturbative expansion around a symmetry breaking vacuum. Okay, so if, for example, you take the ON lambda phi 4 in 2 dimensions, in the broken phase perturbative theory can have some sort of renormalon effects, but for Sine-Gordon and all super normalizable theories, in general, you are not going to have this effect. So that's why, for example, if you try to do the same kind of calculation for super normalizable theories, or say perturbations of conformal field theories, massive perturbations of conformal field theories, a la samological, you are not going to find these effects. And so again, when you really want to understand these kind of things, the walls of integrable theories collapses a little bit, and these are the models they have to look at. And these are the models that have, in a sense, the less developed. The integrability techniques for these models are less developed. For example, at finite temperature, there are tons of results about perturbations of conformal field theories, and you can, you have a lot of analytic control. But for these models at finite temperature, the results on integrability are relatively recent. Right? I mean, these are again results by Kazakov and Vieira which are very, very interesting, but they have not been developed analytically very much. So asymptotically free theories in two dimensions are really still largely unexplored in many senses.
Okay, thanks.
Yes.
Thanks for the talk. Two quick questions. So the first one, do you have a physical intuition about Renormalons? You know, for example, instantons, you can consider the Euclidean actions of the classical equation. So do you have a physical intuition about them?
Well, no, I don't think this is actually one of the main open problems. But it's a deep problem. Let me give you a little bit of history. Now, in the 70s, when people discovered instantons, people were convinced, many clever people were convinced that instantons would give you a lot of information about the standard quantum field theories in infinite volume limit, right? So people like Polyakov, David Gross, many people thought that instantons would give you a handle on how to understand non-productive physics. And all these things were, all this hope was eventually completely unfounded. We don't think, it's probably not true that the vacuum of Yang-Mills theory or any asymptotically free theory has anything to do with instant. And this is no. And I have to say that people working on supersymmetry and string theory are have like a wrong bias here, because they think that instantons are very important, but in real life, instantons are completely unimportant. I mean, in asymptotically free theories, instantons do not give you anything, essentially. So saddle points are very much under control, but they give you very little things. And that's and renormalons are, in a sense, the kind of the most our only hope of having some insights on the non-perturbative dynamics of these theories, starting from perturbation theory, because they appear as Borel singularities and so on. But we don't really know if they come from saddle points of the path integral. So I wouldn't be sure. I mean, some people think that, you know, eventually one will find a semi-classical description of renormalons, but I'm not so sure, because we know that the vacuum of asymptotically free theories is not understandable by instantons. So I think we have to actually accept that there are many questions in quantum field theory that do not have a real semi-classical answer, right? And renormalons might be one of them. So, but of course, you know, this is an open problem. If somebody tomorrow finds a good description of renormalons, then I will be very happy, right? I mean, a good semi-classical description of renormalons with the path integral. But and some people have been trying very hard to do this, but I don't think this is really is going to succeed. So what I would like to do is to have some sort of prescription to compute the transeries order by order in the coupling constant, which would be similar to renormalon, to instanton calculus, but maybe, you know, using some different rules. And there are some rules that already exist. For example, you have if you want to calculate if you calculate the product of two operators and you can use operator product expansion, then you can actually get do some sort of diagrammatic calculation of renormalons. Okay, so this has been known for a long time. The problem is that this only valid if you have an OPE. For example, for this observable f of h, there is no OPE that you can use. So there we don't really know at all how to do this. So sorry, this was a long answer, but to make it short, you know, there might be a semi-classical description of renormalons. Right now, we don't know it, and I'm personally, I'm skeptical that it will be ever found.
Okay, yeah, thanks. Second question, if I can,
yeah.
It's much more stupid. If you consider just this perturbative series in classical field theory, just say, I don't know, I compute scattering in a Coulomb background, right? I can compute the series and I can compute the exact solution. There, I guess I know that is the exact answer. And so I do have control about the non-perturbative setup. Is this always clear, like in this kind of classical perspective, with classical particle physics and fields? If I can have classical equation of motion, that I do have control about the non-perturbative part. I hope
you're thinking about doing quantum calculations in classical background fields, more or less, if I understand correctly.
For example.
Yeah. Well, there you can, for example, there are some, people have done, for example, some calculations, in, say, for example, the Euler Heisenberg Lagrange.
I can make another example. I mean, for example, you can solve, I mean, you consider this problems in which the S matrix is solvable is very nice, like it's integrable. And there are other cases which is solvable, like some classical limits, for example, the probe limit, I don't know, and take the classical limit and the scattering in a background. And these you can resum and you know there is an answer.
Yes.
An hypergeometric function or something like this that you can expand.
Okay, but is the series divergent as well?
Well, I mean, it arises from the S matrix in a standard way. That's what I mean. Like usually,
what happens sometimes is that you have observables which are under control that have, for example, since you mentioned hypergeometric functions, that have an asymptotic expansion at weak coupling, and they have a convergent expansion at a strong coupling. This happens quite often. So essentially weak coupling, sometimes is the worst thing you can do, but it's the only thing for which you have like general methods in quantum field theory. But yeah, you can have say strong coupling expansions which are convergent and add up to some sort of hypergeometric function, and then this has also a kind of weak coupling expansion which is factorially divergent, but you know how to solve it because you have the exact answer. Yeah, this can happen.
Yeah, but in this case, it makes contact with the class calculation on a background. That's what I was
but
referring to.
There you can also have some sort of instanton explanations in some cases. I mean, I'm not that familiar with those examples. For example, you consider the Euler-Heisenberg-Lagrangian. It's known that the Euler-Heisenberg-Lagrangian can be understood as an effective theory which has a weak coupling expansion, and then this weak coupling expansion is divergent, and you can resum it in appropriate ways and so on. Yeah.
Okay. Thank you.
So, Predrag.
Yeah, I have two things to say. One is that for me, gauge theories are totally different from all the models we have discussed today. It seems pretty obvious, starting with gamma function, that you get asymptotic series and Feynman diagrams are just glorified version of corrections to gamma function in higher dimensions. So expect factorials and expect something like that. Now in gauge theories, the object, I believe, of interest is not individual diagram. Feynman diagram means nothing. The object is a gauge set. Now the number of gauge sets grows as a power with the order and perturbation expansion. So if you have any bound on gauge sets, and now I'll take Renormalons aside because they bug me really very badly because they don't fit nicely in what I'm telling you. But the gauge sets, if there's any bound on them, this should be a finite theory. You should be able to do it. Now, I haven't been able to do that myself, but there's some numerical evidence from QED. The second remark is that when you're interested in strongly coupled theory, I think you should not start from integrable models, but from anti-integrable models in sense of Serge or Brie, in which there's an interesting limit when coupling is very strong, where things get simple, just like there's an interesting limit when coupling is weak, where things look like oscillator. And basically, in one case, you're dominated by oscillation. In other case, you have hyperbolic structure or chaos or whatever. So none of these things you address, as far as I can tell.
No. Yeah. I wish I could address some of these things. Yeah. But going to your first question, I agree with you that it's hard. That's why I think it's good to go through the evidence for Renormalons in detail, because just generic arguments are not enough. But I think these calculations in lattice perturbation theory are quite convincing that for some observables there are definite Renormalon singularities, right? So this actually grows factorially, and so I think these are the calculations that I would say are telling me about the existence of Renormalons. But now going to integrable models, I think. First of all, it's true that this is not the most. It's clearly a cheap, an an easy contest, but it's still amazing how many things we don't know even in that contest. For example, we're very shocked that this prediction of total Parisi was actually not correct for the location of the singularities. So many of the standard lore that people accumulated about Renormalons in the 70s and 80s, I think, is actually not on very solid foundations. So looking at a solvable model is at least good in order to tell you about counterexamples to a conjecture, right?
Totally agree.
Yeah, and then, you know, if we cannot understand Renormalons, which definitely exist in the nonlinear sigma model, I don't think we will be able to understand it in QCD, right? So I think it's still good to look at these models. And
absolutely,
yeah.
and you know, I have the same problem as Ricardo. I don't understand. I have no intuition about it. And it bugs me to no end. And you know, your calculations are very important and wonderful. Yeah.
Yeah, can you clarify what you mean by these anti-integrable models?
Yeah, you know, Serge Aubry is a good mathematical physicist from Paris, but it comes from studying, you know, Frankel, Kontarova, and many models in condensed matter physics, where you're on a discrete lattice, and you know, I mean, Harper's model, I don't know,
I see.
almost anything like that, and you're interested in you have some coupling constant and some limit. They're just like a matrix oscillating, but then they get uncoupled. It's more complicated than a nonlinear, you know, quartic oscillator because it's a lattice, coupled lattice. And then there's a whole body of work by Robert McKay, Mies, but Serge Aubry started it, in which for these models, when you take coupling very large, it's actually doable, you know. So the physics of it is you have kinetic term balancing the potential term. And what we do in your kind of perturbation theory is say like kinetic term is important, the integrable term. And then there is this stuff on top of it, a little stuff, which is, you know, 1 over fine structure constant that has to be added correctly. Now, in that other limit, potential is everything. And this kinetic stuff, that's called anti-integrable limit. And it's also very simple.
I see. So it's more like it's more like a strong coupling limit, right?
Well, it's very specific. It's not that it's, you know, strong coupling limit, but you have a organization of saddles or solutions on there, and they're basically all hyperbolic rather than
I see.
when they're down there.
I see. No, I agree. I completely agree.
You know, it seems like a better starting point. You know, that's the thing about nonlinear dynamics.
Yes,
if you're looking at planets, moons, it's a good thing to have little oscillations on top of big ones. If you're looking strongly chaotic systems that mix very strongly, that's not where you want to start. You want to start at the end, where you have strong stretching, folding, etc. It has totally different structure. The saddles, that's called Gutzwiller theory of.
Yeah. So this is
there's exponentially many saddles. They're actually rather simple. Individually, you have to learn how to sum them up.
So this is just the periodic orbit theory, the story of periodic orbit theory, and so on.
One example is periodic orbit theory, but the basic idea is that when you have strong coupling, you have many solutions. Yeah, it's like turbulence. You don't have just few solutions.
I see.
And small corrections on top. So it's a totally different way to approach the problem. And each saddle point is kind of saddle point that you say, you know, it's asymptotic theory. If you go beyond WKB around it and start expanding, you will have to worry about it. But they make up by being dense and ergodic in every place. So in Gutzwiller theory, you start by computing the first contribution to saddle point, and it's good. It's a pretty good approximation.
I see.
But you know, you start. I'm sorry, from anti-integrable, not my word. It's,
Yeah, this is something that I would like to understand better. All these I mean, I have your papers on, I have your book on chaos and your papers on periodic orbit theory.
Well, it has to be rewritten like everything else because now we normal
I
ones
have them on my
better done.
desk to understand them better. Yeah. I don't know if there are more questions or.
If not, let's thank Marcos again. Very nice talk. Thank you very much.
Thank you. Thank you very much.
Thanks a lot. I love your talks.
Bye. Okay.